So let's talk about finding an equilibrium point of a nonlinear system. So the linear system, or the nonlinear system I want to look at, is what's called the Lotka-Volterra model. So this is a simple model for predator-prey calculations. So if you have a certain number of predators and a certain number of prey in a particular population, how is that population going to vary with respect to time? So the equations for this are fairly straightforward. We're going to use the variable x1 as the prey population and x2 as the predator population. And then we're going to express the rate of change of x1 and x2 with respect to the internal variables of the state and some constants. So we want to, by the way, constrain that we are anticipating that x1 will always be greater than or equal to 0, as will x2. So this is just a sanity check. We never expect that we're going to have negative predators or negative prey. And so in order to make this match with reality, we make this assumption. So Lotka and Volterra developed these two systems of equations. So x1 dot is ax1 minus bx1 x2. And then x2 dot is minus dx2 plus c x1 x2. So right away you see we have a couple more constants here. These constants a, b, c, and d are all assumed to be greater than 0. This is very important because if we choose different constants here, we're going to get different linearization points. We could get a lot of different linearization points, depending on whether we chose some of these values to be 0, for example. So this is an important assumption, and it's necessary for the equations to work anyway, so let's preserve that. So what I want to do now is find all the equilibria of the system. So what are the equilibria that you might ask? How do we get those? Well, the equilibrium is where you have some x dot equal to 0. That is, the time rate of change of your system is equal to 0. So we can go ahead and write that down for system x1. So x1 dot is equal to 0. That's the condition for equilibria. And now we look at the value for the equation that we have for x1. So x1 dot is ax1 minus bx1 x2. We can take this to the next level and move the bx1 x2 to the other side. So this is one equilibrium condition. Anytime this condition is met for values of x1 and x2, we're going to be in equilibrium for the equation x1 dot. For x2 dot, again, we set it equal to 0. This is the value that we have for the time rate of change of x2. So now, thankfully, one of these has a minus sign. We can go ahead and move it to the other side. dx2 is equal to c x1 x2. So there are actually 2 points of linearization that we have here. We could choose x1 equals to 0, and that satisfies the top equation. But there's another solution too. We could also choose x2 equals a over b. So for x2 equals a over b, we get on both sides ax1 equals ax1. So for any value of x1, as long as x2 equals a over b, this particular equation is solved. For the second equation, we can again choose x2 equals to 0. So if x2 equals 0, we're now able to find the linearization point for x2 dot. An alternative is x1 equals d over c. So whenever we make that decision, then we have dx2 equals dx2. So then for the second equation, we can choose any value of x2 as long as x1 equals d over c. But those are for the two equations independent of one another. We need to combine these together to come up with the actual linearizations. The actual equilibria points. So our two equilibria points are x1 equals 0, x2 equals 0, and x1 equals d over c, x2 equals a over b. So I leave it as an exercise to you to check, is it actually an equilibrium point if we choose x1 equals 0 and x2 equals a over b. So try substituting that in to see whether it's actually an equilibrium condition for both x1 dot and x2 dot. Okay, so our first equilibrium point is x1 of 0 equals 0, x2 of 0 equals 0. The second equilibrium point, equilibrium 2, is x1 of 0 equals d over c, x2 of 0 equals a over b. So if we choose these two values, our system will be in equilibrium, whether we choose equilibrium 1 or equilibrium 2.